Welcome to Wings of Arrow Advanced Education and Research Organization. To know more, visit our official webpage www.wingsofarrow.in. Now we are going to learn about how to find the heat transfer over a moving plate. Consider the two plates are separated by a distance of 0.01 meter. The temperature of the two plates is equal at a value of 288 Kelvin, standard sea level temperature. The air pressure is constant throughout the flow and equal to 1 atmosphere. The upper plate is moving at Mach 3. The shear stress at the lower wall is 72 Newton per meter square. This is about 1.5 pounds per square foot, a much larger value than associated with the low speed case. Calculate the heat transfer to either plate. Since the shear stress is constant throughout the flow and the plates are at equal temperature, the heat transfer to the upper and lower plates is the same. Given data. So here temperature of the plate TE is 288 Kelvin. Constant air pressure throughout the flow PE is 1 atmosphere and Mach number of the upper plate ME is 3 and shear stress at the lower wall tau W is 72 Newton per meter square. Prandtl number PR is equal to 0.71. Now the question is, what is the heat transfer to either plate? In fluid dynamics, QF is the flow of a viscous fluid in the space between two surfaces, one of which is moving tangentially relative to the other. So let us define a heat transfer coefficient for adiabatic wall as QW dot is equal to rho E into U into HAW minus HW into CH, where rho E is the air density, UE is the velocity of the upper plate, and HAW is the adiabatic wall enthalpy, HW is the specific heat enthalpy, and CH is the Stanton number. So now here all values are unknown. First find rho E. From the equation of state we can write rho E is equal to PE divided by R into TE, where we know pressure and temperature values, they are given. So where R is the gas constant, which is 287 joules per kilogram, substitute these values in this equation. When simplify, thus air density at both plates is 1.22 kilogram per meter cube. Second, find the velocity of the upper plate UE. We know that the Mach number is the ratio of velocity of vehicle to the speed of sound, which is m is equal to u divided by a. From this we can write for velocity. Then ue is equal to ma into ae. We know m is 3 and we can find speed of sound ae from square root of gamma into r into te, where gamma is the heat capacity ratio, which is 1.4. Substitute these values and solve. Thus UE is equal to 1020 meter per second. Find CH. From Reynolds analogy, Stanton number CH is a function of the Reynolds number and Prandtl number. It is one of several different types of heat transfer coefficient that is used in the analysis of aerodynamic heating. It is a dimensionless quantity. We can write CH is equal to CF divided by 2 into PR, where CF is the skin friction coefficient and PR is the Prandtl number. We can define skin friction coefficient as CF is equal to tau W divided by half rho E UE square, where we have all values. So now substitute those values in this equation and solve. So CF is equal to 1.13 into 10 power minus 4. Now we can find CH. So substitute CF and Prandtl number value in CH equation, then simplify. Thus we get CH is equal to 8 into 10 to the power minus 5. Then find the adiabatic wall enthalpy HAW. The heat transfer depends on the wall temperatures and amount of viscous dissipation. For incompressible and compressible quiet flow with a constant Prandtl number, the adiabatic wall enthalpy is HAW is equal to HC plus PR into UE square divided by 2. Here the pressure remains the same. From the derivation of the enthalpy equation, the specific enthalpy is equal to the heat transfer for a constant pressure process. We can write H is equal to Cp into T, where Cp is the specific heat of air, which is constant 1004.5 joules per kilogram per Kelvin. Now substitute the appropriate values in this equation and solve. Thus we get HAW is equal to 6.59 into 10 to the power 5 joules per kilogram. One more unknown value is there. So find HW. We can know that HW is equal to Cp into TW. So substitute the values and solve. Then HW is equal to 2.89 into 10 to the power 5 joules per kilogram. Finally, we have the required values to find the heat transfer coefficient. So substitute the values in QW dot equation and simplify. Thus the required heat transfer is Q dot W is equal to 3.68 into 10 to the power 4 watts per meter square. Did you know? The first man up on the balloon was also the first man to die in one. Unfortunately for Francois, his tenure as a hot air balloon pilot was short-lived. A couple of years after his successful test flight, he decided to move on to more ambitious projects. He designed a balloon which he claimed would be able to cross the English Channel. His claim proved unsuccessful and fatally so, unfortunately. The new balloon stayed afloat by using a mixture of hydrogen and heated air. Francois' mistake was to underestimate the explosive potential of the former of these two gases, particularly when heated by the latter. Thus, midway across his voyage, his craft exploded, killing everyone on board. Hot air balloons cannot fly in the rain. As well as interfering with visibility, the rain cools the balloon, meaning more heat is needed. What's more, it adds additional weight to the balloon and runs down the sides, dripping onto passengers. The singer Newton Faulkner once played a gig in a hot air balloon above the Swiss Alps. The event was for a UK radio station.
If you have further inquiry or requested video, drop down to our mail wingsofarrow@gmail.com. Don't forget to subscribe for more updates. For the time being, take care, stay blessed, inspired, and fly high.